oops, that was a mistake right there. Let me erase that. Okay. All right, this is a problem that, let me switch it up. This is a problem that's a goodness of fit test, chi-square test. So the number of AIDS cases reported in Santa Clara County, California, is broken down by race in the table below. So these are reported cases. These are what we call the observed cases. And they also give us a total. So that is our N. That's the total number sampled, or 3,971. Okay, so then they said choose the correct null and alternative hypothesis. The null hypothesis in a chi-squared for goodness test is always that it follows the distribution. The random variable follows the distribution. So let's figure out the distribution of AIDS cases is different. Nope. The distribution of AIDS cases is consistent with the race distribution. Okay, so this is the one we want, is the second one here. And the alternative hypothesis is always the opposite of that. The AIDS cases is different from the race distribution. It always helps me remember which one is the null, because that is the one we're assuming to be true. So if we assume that it's consistent with the proportion that they believe to be true, then we're going to take that proportion in a decimal form and then multiply it times the total number sampled, and that can give us that's how we're going to calculate these expected counts. That's in part 2, they ask us to calculate these expected values. So all I did was I took the N value that we got up here, the 3,971, and I multiplied it by each proportion. So I put 0.46 times by the number of sampled, and that gave me, so this is the distribution in question in this table. Let me see if I can get my pointer. Okay, so see this, this table here is giving us the distribution in question. They believe that 46%, written as a decimal, 0.46%, is white, and 25.1% is Hispanic, and so on. This is the believed distribution that we're trying to test. So if in case this was a true distribution, then if we sampled 3,971 people, then if 47% of them are going, we expect 46% to be white, then 0.46 times 3,971 would mean that we would expect 1,826 people, 0.7 people, actually. We can't have 0.7 people, but whatever. 0.7 people would be white, and so on. So all we did was take these decimal values and multiplied it times the 309, our N value, which was 3,971, and we got these expected values. We can double check our answers in this case, in this situation, but oh, I guess I can't easily double check them, but anyways, that's what we get. Okay, then I entered in both the observed and I entered the observed in my L1 from up here on the top table, and then the expected ones that I just calculated, I entered them in L2. To do the hypotheses test, we can go to stats, we can go over to tests, and we can go down to chi-square goodness of fit test. I did put I just want to make sure that the observed are in my L1. I did do that, and the expected are in the L2. I did do that. The number of degrees of freedom. Degrees of freedom is the number of categories of the random variable -1. So there's white, Hispanic, Black, and Asian. So that's 4 different categories. So 4 minus 1 is 3. So our degrees of freedom here should be 3. And then I just press calculate, and that's weird the way they have the answer here. Let me see if I can. Okay, I just had to make it bigger. So our chi-square value is 2121, which is really large. And the p-value is 0. So it's telling this is a right tail test. All goodness of fit tests are a right tail test. So it's telling us that the chi-square distribution always kind of looks right scaled. Sometimes for large values of n, it does start to look normal, but I just draw it as right tailed always. Guess it doesn't hurt. And the value here is way over here at 21,000. This is 0 on the x-axis, and this is 21. It's extremely far down in the tail, if you will. And then the area under the curve is so small that it's actually a 0. But I'm just drawing it so you can see something, but it is so tiny actually that it's 0. That's what's happening with this test. So we would put here 21 to 1 decimal place. It'd be 0.1, and then to 4 decimal places, this is just 0. And if they want 0, it could be 0.000. They're going to be choosy about having 4 decimal places. And then it says interpret the results of this. So definitely, because the p-value is 0, it is less than alpha. So we always have to ask, is the p-value less than alpha? Yes, it is, because it's less than anything, because it's 0. So we're going to reject the null hypothesis. And that means I'm rejecting the fact that it's consistent with the distribution. So we think the distribution of age is different than the race distribution. So it is the differences between the distribution. Okay, let's read this. The differences between the distribution of AIDS cases and the distribution of the general population is not statistically significant. No, it is. We always say it is statistically significant if we reject the null hypothesis. The differences between the differences between the distribution of AIDS cases and the distribution of the population is statistically significant. These differences are really large. So the differences are also important from a practical perspective. For example, the number of Blacks is more than the Asians with is less than expected. So there we go. So this second, and I can just double check the answer. Okay, so we can double check our answers here. Yeah, see the value is 2221, the p-value is and the differences between the AIDS cases and is statistically significant. The differences are also important for practical for practical information. So there we go. There is our test. So it actually was the second one is the one that we wanted to choose here. Because the distributions are different. All right, have a great day. I hope that makes sense.